Okay, let's get started. Thank you all for coming. I'm still coughing, and especially when I talk, I cough more. So today we will keep talking about format string vulnerability, and we will look at the very interesting percentage n. And next week we will talk about one of the most interesting topic in software security nowadays, which is return-oriented programming. So next week I will make sure I will be there in person, because that one is a little bit tricky. And for most of you, even though you are familiar with software hacking now, and even format string may look natural, but that a return-oriented programming will be a little bit counterintuitive at the beginning. So it's actually very fun. So I will make sure I will be there next week. However, the week after next week, I will be traveling again, so I will be delivering the class online again. Okay, so this is format string level 3, where you guys did in your homework, and I showed you the demo last week. So in this one, we have two local variables, buffer1 and buffer2, and the vulnerability is actually in the sprintf, not in the fgets. The fgets here doesn't really have any vulnerability. It will only input to the buffer2. The buffer2 is 100 bytes, and we're only reading 100 bytes. So you cannot overwrite anything. You cannot overwrite buffer1 from buffer2. However, we are treating whatever is in buffer2 as the format string. In sprintf, the second one is the format string. The second argument is the format string. The first one is the target. So which means our format string doesn't have to be 100 bytes long. Our format string can be even smaller, but the string generated from format string can be arbitrarily long, right? That means we can overflow that buffer1, which is only 100 bytes. So that is flag 3. So today we are going to look at only 2 examples, but we are going to look at 2 different ways to capture the flag. The first example is simple program. We have a global variable os, which is initialized to the value 0 at the beginning. This is a global variable, so it's initialized to 0 before the main function is even called. Then we have a vol-foo vulnerable function. Vol-foo has a local variable 512 bytes, how big. Then there is a fgets to get from std in your input, whatever your input, then put in this local buffer. So this part, no vulnerability, same as format string 3. The buffer is 512 bytes, and we're only reading 510 bytes, so you're not going to overwrite anything. However, the vulnerability still is the next printf function, which use your user input directly as a format string. And because of that, you will be able to print out anything on the terminal. However, different from the previous one, different from this one, you're not going to put the generated string in buffer1. Not going to do that. The generated string will be directly output to the terminal, right? So it's a different vulnerability from the first one. You cannot use the previous approach to overwrite the return address on the stack for vol-foo. The main function is simple. It calls vol-foo. Then if it checks if the auth variable has been changed. If it has been changed, then you can print flag. Otherwise, the program just doesn't do anything. All right. So the idea here is very simple. There are 2 ways to do this. We're going to look at the first easy way, using percentage n first. Before that, let's take a look at the stack of this program. So this is W12. At this point, I believe you are already familiar with the disassembling of a function. We have the standard prologue of the function, and this part is for the position-independent code to get this line of instructions runtime address. Then it calls printf. It does other things. It calls fgets, and it calls printf again, right? Well, there is a condition, depends on it calls this, which is print. Oh, that printf is probably, what is this printf? Okay, it's possible that this disassembly is not the latest version. Anyway, so from this, you can get the buffer's size. You can compute where is the buffer. But from here, we already know that we're not going to overflow this. So the idea is same as format string 3 or previous challenges. The place we can put our format string in is at the beginning of the buffer. We can put in our format string there. Then the printf, we can use %x or other percentage, blah, 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 whatever, to look for our input format string, right? Because the printf function stack will be at a lower address, and it will look for its own arguments, and use %x or other things. We can always go up several bytes, 4 bytes, 8 bytes, and to make the format string here corresponds, or string here corresponds to our format string, right? So that's the idea. So our idea will be something like this. Our format string, our input, our exploit will look like this. At the very beginning, it will have the address of that global variable auth. Then it will have many %x there. This %x is basically to skip the items on the stack. The ultimate goal is to have a %n there corresponds to the address of the global variable auth. So the %x will correspond to other things which has a lower address of the address of auth. And those other things we do not have control of. We don't really control them. So if we can make that %n corresponds to our input address of a global variable authenticate, then the printf will change the value stored in the authenticate, the auth global variable, making it not 0 anymore. As long as it's not 0, the program is going to print the flag false, right? That's basically the idea. Does that make sense? So let's see how that works. This is overflow, not overflow. Format string 5. So those challenges, 64-bit version or 32-bit version, they're the same anyway. But we use 64-bit version, so they are easier. The address you need to input will be basically shorter. So let's do a we just run the program first, right? The program actually tells us where is the return address. Oh, the reason we print out where the return address is for the second approach to exploit this. the first approach, we only want to print out just want to overwrite the value of os. Okay. So how do we do this? Any idea? First of all, this program takes format string. So then let's just print a format string. Let's just feed a format string to that. Let's feed a %x there. Let's put a several. Let's put maybe 3% there. All right, that's our format string. Then format string, we feed this into the program. So what will happen? When we do this, we put a 3%x here. Then the printf function will have 3%x here. So it will look for 3 arguments on the stack, which should correspond to that. But we didn't give those arguments. We didn't give that input, which means it will print out something random on the stack, right? For us. Oops. See, it print out 3 things on the stack for us. If we have more of this, obviously it will print out more for us. So we can pick what is on the stack. But that is not only what we want to do. We also want to put the address of os at the beginning of our. You don't have to put it in beginning, but it will be easier. We put it at the beginning of our buffer. So we need to find out where is the global variable os. Let's say if it's static. Compare this one, linked. Oh, maybe yes, right? So we just do a name. You can say, oh, the os is at this address. This is a fixed address. Then we put this address at the beginning of our buffer, which is 34 30 0408. Okay. So now we do this again, and we put this address at the beginning of our buffer. So we have many %x there. So eventually, one of the %x should show us the address, right? Because we put it there. Because the %x will start looking for things at a lower address, then move up, 4 bytes, 4 bytes. Eventually, it should show us the address of whatever we put there. May not be sure that 4 bytes, but part of that 4 bytes, like 3 bytes of that and another 1 byte. If we say something like that, we can easily adjust anyway. So let's see what we get here. So if we do this, do we find the address we are looking for? No, right? We already put how many? 1, 2, 3, 4, 5. We put 6 here, but looks like we do not find the 1. Do we say 34 here? We don't say 34. Okay, so means we probably need to do, oops, put a little bit more here. Here, you see, here we have this address. Eight zero 0804 C034. That's the value we put there. Okay. I can prove that. Let's change that value. Let's change this value. Instead of 34, we change to FE. And you can see this value changed because that's the value we put there. It's not the value which was on stack originally. Right. So now we have this 34 here, which means what? Means we don't really need so many %x. So this is the first %x, second, third, fourth, fifth. 4 is fifth. 0 is sixth. Seventh. The seventh percentage X corresponds to that address, which means we just need to change the seventh percentage X to percentage N. 1, 2, 3, 4, 5, 6, 7. Oh yeah, sorry. Right? We just need to change the seventh percentage X to percentage N. Then this percentage, instead of percentage X, percentage N will correspond to this address. Then what does this do? Percentage N will ask print F or any format string print to write how many bytes have been written, the number of bytes, how many bytes have been written to that address. Then let's get a feeling how many bytes have been written here. Basically, how many bytes is starting from this bytes. Those many bytes have been written there, right? Some of them could be not visible. I think here everything is visible actually. Yeah. The percentage X will just show the number, right? Also dot count. So here we have probably 20 something. So 20 something bytes have been written so far, which means at this address, we are going to write the value 20 something. That will change the value of auth. And because of that, we are going to pass this check and print flag. Yeah, that's it. So let's try. Okay, that's how it works. So you see the percentage N here is a very, very powerful tool for attackers. You can use this to write at arbitrary address in the address space. Anywhere in the address space you can overwrite. It doesn't have to be on the stack actually. So this is more powerful than the attack we learned in the first half of the class, right? The buffer overflow. The buffer overflow, you can only start writing at the buffer, and the buffer is on stack. And you can only do a sequential writing. You cannot skip the stack canary. But here, you can write any address. You can write 4 bytes, you can write 1 byte. So it's more powerful. So Alex, you have a question?
Yeah, I'm sorry. I think I missed it. How did you get the address for auth?
So the address for auth, I actually used the tool NM to do that. You can also use, you can just debug and print out.
Okay, thank you.
Yeah. So this program is statically compiled and linked. That's why the address I get from NM is the final address.
Oh, sure. Okay.
Yeah. So that's the first example. Okay. Easy, huh? Okay, let's take a look at our second example. After that, we go back to the first example and think about another approach to attack the first example. We already know that we can do arbitrary write. Okay. The second example here is just a change from the first example. Here we have 2 auth global variables, auth and auth1. They are both initialized to 0, and they are global variables. So both of them are at .data section or .bss section. They are not on stack. The val-foo is actually the same as format string 5. You can input a long format string, and printf will directly use that format string. The main function first call val-foo, then print out the number of auth and the number of auth1. And it checks that if auth has a value 60 and auth1 has a value 80, then it print out the flag. That's it. So the idea here is simple. We are going to override both os and os1. However, os, we have to override it to 60. os1, we have to override it to 80. And we have a constraint, remember? We cannot directly determine, we cannot directly say, I want to write this value at this address. We cannot do that. We printf will only, or any other print, will only write how much data, how many bytes of data has been output so far, that value to the percentage n corresponds. Okay, so we do not directly control. You cannot directly say move 60 to os1. No, but you can print out 60 bytes, then have a percentage n corresponds to the address of os1, os. Then os will be updated to 60. Then after that, you print out another 20 bytes, right? After you print out another 20 bytes, you have another percentage n corresponds to os1's address. Then in total, we have been printing out 80 bytes. That's why os1 will be changed to the value 80. So that's why in the homework, I ask you guys to write a program to use different format strings, use multiple percentage n, so you can understand how percentage sign n works. Okay, then let's go back to format string 6. Format string 6. So we use the same approach. Let's just print something out to see if it works first. Okay. We feed 2 percentage x to this program. The program will send out 2 values on the stack for us. And we didn't change os1 and os2, right? And we use nm again to find out os1 and os2's address. Do we have it? Yeah, here. Those are the 2 addresses. So it doesn't really matter we override os1 or we override os2 first, right? Doesn't really matter. Let's do both ways. Let's try to write os first, then write os1. But there is a tricky thing here. You can see that os1 has a value 60. Os has a value 60, but os1 has a value 80. So if, let's say, we want to write os1 first, then we have to output 80 bytes. Then after that, how can we still write os for 60 bytes? How do we do that? Because we already override 80 bytes. How can we bring it down back to 60 bytes? 60. Any idea here?
Couldn't you just use another %n because then it would just reset the number back to 0?
No, percentage n doesn't reset. As long as it's the same printf function call, it doesn't reset.
Okay.
When you say that reset, that's because you call the printf or format string function multiple times. But you're thinking, that's good. Any other idea? Just guess. I mean, so one thing I want to teach you guys is, even though we are computer science students, most of the things we are doing is engineering, right? So since it's engineering, it means there is a way out. There is always a solution. And for hacking, the same thing. There is always a way. You just need to explore all the passes. Okay. The idea here is to overflow the number. Because os is only, any integer here is only 4 bytes. Which means if we overflow that, then you can get a 60 again, right? But of course, if you want to overflow 4 bytes, that's a huge number. Then maybe you do not overflow 4 bytes. You only overflow 1 byte. Which means we're not going to use percentage n later. Because percentage n, we're write 4 bytes. We needed something to only write 1 byte instead of 4 bytes. And actually, the format string conveniently provide us a tool to do that, which is the HH. So using this, instead of using percentage sign n, we use percentage sign HHN. It is still look for 4 bytes of address, but it's not going to overwrite 4 byte of value to that address. It will overwrite 1 byte of value to that address. And we can only overwrite, let's say for OS1, we first do 80 bytes there. Then we only overwrite 1 byte of OS, the least significant byte. And we do not overwrite 60 to there. We overwrite 256 plus 60, right? Which is 316 there. So to overwrite OS1, we already print out 80 characters, 80 letters. Then we print out a little bit more, right? 296 more characters. That will make our total number of numbers we print out will be 300 something. But 300 cannot be represented by 1 byte. It's overflow that. And we only take the least significant byte. So we get 60 again, right? But let's do that later. Let's do the easy one first. Let's do the OS 60 first. Then we do OS 180. Okay. So we find out the address of those. Then we try to put those address here. We need 2 addresses. So those approaches work for both 64 and 32-bit, but 32-bit is just easier. So I always choose 32-bit in a class. 0, 04, 08, then 38, 0, 0, 04, 08. Okay, if we print all this, we have multiple percentage x. When we have multiple percentage x, eventually we will see the value we put there. See, it's here. 34, 38. That's the value we put there. So let's say for the first one, OS 30. That's the 1, 2, 3, 4. That's the 4th percentage x. So we can change that to percentage n here. Okay. So now you can see that OS has been changed. However, it changed to a big number. It's 29. That's oh no, it's small, still smaller than we want. Yeah, what the number we want is 60, right? So how do we change this to 60? Any idea? How do we change this to 60? How many bytes are here? Here we control this. This is basically 8 bytes. This one, we don't know how many bytes, right? Percentage n, and there's no filling. If it's a small number like this one, it's actually a small number. It only print out maybe 3 bytes. Yeah, 3 bytes with a dot, 4 bytes. So it's not something we can we are easily controlling here. So to make this more controllable, then we can just change this. Remember how do we change this? We just put a number here, right? Then we can tell how many. Let's use. We don't have to use this fitting actually. For example, if we don't, we just put 8 here, which means the first one we're going to print out 8 bytes. Okay, but it will use white space to fill the gap there. Make it easier to understand. Instead, and let's put, oops, 0, 8 here. So it will print out 0, 0, 0, 0, then YFE there, right? So by doing this, we can actually control how many bytes we want to output. So let's just use all of this. Okay. So after this, you can see that we print out how many? 35. Okay. So why is there 35? Here we have 8. This is 8. This is what? This is 9. Okay. Because the number is 8 bytes, then we print a dot there as well. That's 9. So we have 3 of those, right? 3 of those, that's 27. 27 plus 8. So this part will give us 35 bytes, right? And we want to make it 60. That's easy. Well, for one of them, we just we need how many? We need another 25 bytes. So we just add 25 bytes to this. 8 here, 8 just plus 25, 33. Make sense? Does that make sense, guys? See, after this, that the value on the stack, we don't care about that value. However, that value will give us, will change this to 60. Why there are 2 dots here? Did I put 2 dots? You guys say why there are 2 dots here? Dots should be 20 or something. So 1, 2, 3, the third one. So we have the first, yeah, this first percentage, second, third. After third one, we have 2 dots. Huh? What's going on? So this one, we don't have 2 dots, third dot. After we change percentage n, we have 2 dots here.
Is it because percentage n doesn't print out the hex value, but it just stores it to the variable?
Yes. Oh, yeah, you're right. Yes. So you're right. So this percentage n will not print out anything, right? So ignore that. That's why there are 2 dots. This dot and this dot. Right? Yeah, you're right. Yeah. So to make it look, better, maybe just let's remove this dot. Okay. Look better. Okay. This way. Yeah. Who was that? Sorry, I didn't get who you were there. But
That was me.
who are you? Sorry,
Kyle.
that's Kyle there. Okay, sorry. Yeah, that's right. Okay, so you can see so far, we changed the auth to 60, and this percentage maps to the first address. Now we have we need to change the second address. If we change this percentage n, the percentage x to percentage n, this percentage n will map to the second address, right? However, both of them will have the value 60 because between them we didn't print out anything, right? So we do this, both of them will be 60, auth and auth 1. So one way to do this is in between we add another 20 bytes, right? Like 20 bytes of dot. That's 5. Like this, right? This should work. 1 percentage n, another percentage n, and in between we print out the 20 bytes. So auth 1 now should change to 80, right? Now it works. But what if it's a huge number? You want to do it a smarter way. A smarter way, you already say that, is you can use percentage, whatever number here, right? let's say we want to do a 20 here. You can do a percentage 0, this 0 doesn't really matter, this 0. Then 20x, then percentage n. But if you do this, let's say we change it to this way, what will happen now? Is this correct? Are we getting a flag this way? We don't really need those two. Are we getting a flag? Yeah, just guess what will happen here.
I think we'll get the flag.
You think we will get a flag? Let's say. It doesn't. Why it doesn't get a flag? So this percentage n corresponds to the first 4 bytes, right, for the address. This percentage x corresponds to what now? Alex, what does this correspond to?
My processor's running a little slow today. Give me a second.
So the first percentage n corresponds to the first 4 bytes, which is the address. The second 4 bytes is another address we put there. But however, that address, that 4 bytes corresponds to the percentage x now. Doesn't correspond to the percentage n anymore. The previous one, it does correspond to percentage n, because in the middle, we don't have any format specifier. See, right?
Yeah,
Which means the percentage n doesn't correspond to the address we want. Instead, the percentage n points to this part and use this part as an address to write some value there. And that triggers the segment fault. Make sense?
yes.
So to do that, which means we need to put something in the middle here to correspond to this percentage x here. So let's add the 4 bytes in the middle. Okay, so that 4 bytes will correspond to percentage x. Then percentage n will correspond to this address. However, after this, things will also change. Anyway, let's try this. Right, now the corresponding relationship is correct. However, the value is different because we put 4a's here. And that 4a will change before we put 4a's, doesn't really have to be a, whatever. 4a's there before the first percentage n. Right? Which means we write 4 more letters, 4 more bytes out. So we need to subtract that 4 from this value, the x, or you can subtract from other value actually. Let's say we subtract from the very first one. The first one we have 0, 8. We change to 0, 4. It works, right? Because the total number is correct. Or we do not subtract the first one, we subtract from here 33, we change to 29. It should also work. Make sense? And that 4a's corresponds to this x, and we printed them out here. That's why I said 41, 41, 41, and a lot of zeros there. Okay. Does that make sense? Cool. So that is how we overwrite OS first, then we overwrite OS 1. Like I said, the order doesn't really matter. So next, let's say, how do we overwrite OS 1 first? Which means the first address should be OS 1's address, 38. Then we have 34. Okay, then we do this. Okay, now OS has the value 80. OS 1 has 60. That's not what we want. We want OS to have 60, so which means let's change OS 1 to 80 first. Our goal right now is to change OS 1 to 80, and we don't care about OS. Okay, so that's actually easy because OS 1 corresponds to, this is OS 1's address, so it should be the first percentage n there, right? So before the first percentage n, we just need to add another 20 bytes. So right now it has value 60. We just need to change another 20 bytes. So 29 we change to 49, right? Huh? What's going on? Where I did it wrong? Oh, sorry. I was using the previous one. The address, this one is correct. The first address should be 38. The second address is 34. Okay. Now we have OS1 80. That's because OS1 is the first percentage n, and this is address. And so far we've been writing 80 bytes. Now the second percentage n corresponds to this address, which is OS address. And we want how many? We want it to be 60. So far we have 80. So we cannot bring 80 back to 60, like I said. But 60 is the same as, first of all, we have to use HN, okay? Instead of N. So for OS1, we use percentage N, we write 4 bytes. For OS, we use HN, half. So so the half of 4 bytes is 2. The one more time half, then we're only overriding 1 byte. And it's the same address because that address is the least significant address of that, right? So, however, the value we're going to override will be different here. So far here has been 80. So now we need to reach to the value of 256 plus 60, because we do not get 60. We only get 256 plus 60. That's minus 80, right? Oops, what's going on? Minus 80, because we already override 80. So we only need 236 more bytes to print out. So here will not be 20 anymore, 236. Okay, still works. But this one has to be half byte. Let's say if we don't do half byte, not half byte, I mean half word. Let's do percentage n there. Then what will the value be? OS1 will still be 80. What will be OS? OS will not be 60. What will be OS, guys? Come on, this is easy. How many bytes we write so far? Write out so far?
Should be 316, I guess.
Which one?
316. Like the value will be 316. Because that'll print the total number of bytes. So.
Exactly, you're right. 316, right? So you have to do half word, which is HN here. So obviously you can overflow this multiple times. You don't need to just overflow it once. So now we have 236. Then 236 plus 256 again, we get 492. That should work as well, right? That should work as well. Or yeah, let's do plus yeah, like this number. 1060. You should work as well. 1060. Okay. Well, the funny thing is when I do this, obviously my screen will be filled with zeros first, right? Because here we're printing like 400 zeros. Now we're printing out 1000 zeros, but eventually it will give us a flag, right? Or even more. So obviously plus a 0 here will also work, right? So this big number, 10,000 something, will be the same. it works. It prints a lot of zeros out, but eventually it gives us a flag. So that's how format string 6 works. So in the homework, you're not only going to do format 5, format 6. I will give you a bonus question for format 7. And that one has 3 numbers to override. So when you need to override 3 numbers, obviously it's a little bit even more constraints, which means you need to use that percentage HHN to do this. Okay, now let's go back to format string 5. The approach I'm going to talk about now actually not only works for format string 5, but also works for format string 6 and 7. But this one is interesting. So like I said, we have a very powerful attack vector here. You can overwrite arbitrary address. You can overwrite 1 byte, and you can overwrite thousands of bytes using this vulnerability. You use a percentage n, you use multiple percentage n, right? Then you can overwrite many things. So in the previous example, 6, you see that we do not have to constrain ourselves to 1 percentage n. We can have as many as we want. So then in the address space of a program, what are the most valuable data we want to overwrite? In the first half of the class, we try very hard to overwrite the return address. And the return address is a code pointer. There are other code pointers as well. But let's say here, we want to use this percentage n to overwrite the return address of W12. We do not overwrite the auth. So the idea is simple. We do not overwrite the auth. Instead, we overwrite the return address and let it to print return to print flag. That's something we did many times in this class, but we were using sequential overriding before. Now we're using format string to override that. And the idea is similar, right? So obviously, we want to override byte by byte, use multiple percentage HN. That will be easier instead of just use percentage n, because the address of the function will be huge. And if you want to get that huge number, you need to print out a huge number of data to the terminal. And that may take forever, right? Could be billions if the address is really high. In our case, it's actually millions. But even millions is probably not doable, right? This program may crash. Yeah, or it may take a long time, several hours, because printing out is really slow. So, but if we do 1 byte by byte, then we, same like the Clary one, we're printing out at most 1,000 something bytes, right? And also, we do not have to override all 4 bytes. We already know that some of bytes will be the same anyway, right? The higher bytes, they will be the same. The higher bytes of the return address originally on the stack and the higher bytes of where we want to return to, they're the same. So we don't need to override that. But probably we will override 2 bytes, I guess. Yeah, at most 2 bytes. If lucky, maybe only need to write 1 byte. Then let's go back to format string 5. Format string 5. We want to find out the address of We want to find the address of print flag. Okay, print flag is this address, and we also want to find out where we should overwrite, right? And this program print out for us the return address is at this stack address, which means whatever is here, we need to override to this address. Okay, as you can see here, the main function, we're overriding the Wolf function, right? The Wolf, not the main. Oh, let me think. Oh yeah, the Wolf calls printf. Main calls Wolf, which means Wolf eventually returns to main, right? Which means on Wolf's stack, its return address will be 0804 83 93 or 94 and blah blah. Okay. However, where we want to go to is at 9236 in hex, which means we need to overwrite 2 bytes. Okay. The higher 2 bytes we don't need to overwrite, but the lower 2 bytes we need to overwrite. Obviously, if the stack is executable, you can even put a shellcode there, then return to there. But this one, as the print flag function is the print flag function is available in the address space, so we just return to there. So okay, let's see how do we do this. We put our address there. We need 2 address, right? 2 bytes. So we put a 2 address there. We need 2 address. What are our address? Let me write down the first address. Then you tell me what's the second address. Okay, the first address I put is the returns address. So what should be the second address? We're only overwriting 1 byte. Any idea? What's our second address? The return. Go ahead.
Print flag address.
Still the flags address?
Yeah.
What flags address? The print flag functions address?
Yes.
No, that's not what we want here. We are overwriting 2 bytes at 2 locations. What are those 2 locations here? The first location is the least significant byte of the return address on stack. What's the second location? What's the second location? Just 1 byte higher, right? Because we're writing the least 2 significant bytes of return address, and this one we're only going to overwrite 1 byte. So just from BC to BD, that's it. No, sorry, B. 8C to 8D, that's it, right? Then we have D6, then we have FF. Okay. So after that, we have percentage X. Let's do this. Let's do a lot of. Next, we need to find out which format specifier corresponds to that. So we need multiple this to find out. Oops, what did I do? Okay, if we pipe this to the program, do we find the address we are writing there? 8C, 8D. No, it's not there yet. Don't have enough. We need more. Let's see. No, it's here, right? FFFF D6 8C. So that's the last 2. So which means the last 2 we are going to change to, instead of percentage X, we change to HHN, right? So the first one, we want to override it to value to, let's do this first. So if we just run this, obviously the program will crash. We are able, so when we do this, we were able to overwrite the return address, but it brings us to some random address and the program will crash, right? And we want the program bring us to the correct place, which is our print flag, which means the last byte should be 36 in hex. 36 in hex is this one. This one should print corresponds to 36 in hex. What is 36 in hex anyway? 36. Let's do hex to decimal.
It's 2-4.
24? No. 36 is hex. Which it should be much bigger, right? It should be 54, right? Yeah, 54. Because 3 times 16 plus 6, it should be 54. 24, you are talking about 24 is hex, then 36 is decimal. Yeah. Here, the value we got here, everything is actually, the value we got here is actually everything is decimal. Is hex, sorry, hex. Yeah. So the value we really want here is what? 54. Okay. Okay, so which means this part has to print out 54 bytes. Let me add a 4. Where's my? Okay. Let me add 4 bytes in the middle first. The reason I added this is the same reason for why we did the format string. What's that? 5. So in between, let's add a percentage 8x here first. Okay. So let's say, so this part is 4 bytes, another 4 bytes, 8 bytes, another 4. So far, that's 12 bytes. Okay, that's 12 bytes. Then this part is 9 bytes. 1, 2, 3, 4, 5, 6. 9. Oh, that's already 9. That's already 55 bytes, right? So far we have been doing 12 bytes plus 54 bytes, because this part, every one of them is 9 bytes, because the address is 8. There is a dot. I put a dot there. We can remove that, but if we do that, everything will be together. We don't know what is what. So this part we have, since we have 6 of them, these are already 54 bytes. So let's say 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's correct. Which means now we have already write 54 plus 12 bytes, but we only want 54, which means then we can add another how many? Basically 144 bytes, right? So 244 plus 12 will be 256, and that gave us the overflow. Then 36. Well, I want to overflow this, right? So which means the last one, instead of doing 8 bytes, let's do 8 plus 244, which means be 252 bytes. Make sense? 252 bytes. So the whole thing here should output, including this dot. The whole thing here should print out 300 10 bytes. That will give us 54 at the least significant byte of this, right? Okay, so far we print out 312, then we overwrite 1 byte. Okay, that's right, 54, which is 36 in hex to that. Then the other one that we need is 92. Okay, the 92 will be what? 92 in hex is 146. Now we already have, not this one. Now we already have 310 here. Then, so we can only write, let's say, 158 plus, what's the value? 146. That's the value we want to write. Minus how many we already overwrite. Not overwrite. How many we already output, which is 310, which means another 92, but this 92 is decimal. Okay. Which means between those, we need to output 92 bytes. Okay. So between that two percentage HHN, we have a percentage X, and we say the length is 92 bytes. I didn't have a dot here. If I have a dot, it should be 91. If my calculation is correct, this should work. Let's see if it's correct. Yeah, it's correct. Good. I'm still good at counting things. Okay, so let's say we just change one. So you see, we get the flag. If your calculation is 1 byte off, let's say instead of 91, we have, instead of 92, we have 91 here, then obviously we jump to a wrong place, right? Yeah. Of course, we can put 2 dots there to make it work, or whatever, the 2 A's here. That 2A will also make the printf print out 2 more bytes, and in total that will be 92. So that should work, right? It works. Make sense? Any questions? So for this one, you need to do some calculation. But like I said, this is an arbitrary override. You can write everything in the address space. There are other code pointers in the address space, like the TLT table we talked about, the GOT table we talked about in the first class. In those tables, there are code pointers. There are code pointers for the C library functions. So let's say the program makes a function call, it will go to that place to look for the C library function's address. But if you override that, the program makes a function call, it believes it's making a function call, it actually gives the control to malicious code. So this is a very, very powerful. This is more powerful than the sequential override we learned in the first half of the class. Okay, so that is that's basically today's work. Is today's class. The homework. Okay. The homework has 3 questions and a bonus question I'm going to answer. The bonus question is already on the server. The bonus question is format string 7. Format string 7. Let's do 32-bit. Yeah, this one. You have to change the auth value to do this. However, there are 3 auth values instead of 2, and you need to figure out what are those 3 values. Because I'm not giving you the source code for this program. Let's do. So in that W12, this piece of code is basically comparing the global variables auth. There are 3 compares, okay? So those are the values. And you can find out the address of them as well. And you need to overwrite 3 of them instead of 2. So that will be the bonus question. Then the other 3 questions are just to replicate what I did here. First, exploit the format string 5 by overwriting 1 global variable. Then overwrite 2 local global variables to capture the flag of format string 6. Then do not overwrite the global variable. Instead, overwrite the return address on the stack to do that. If you overwrite other code pointers, that's fine too, if you know how to do that. Okay. Any questions? First of all, do you guys feel format string is fun?
Yeah, I think it's pretty neat. It's it takes me a minute to like think everything through though.
Yeah. Yeah, the tricky part for format string is the stack layout get more complicated. As long as you understand that, it's actually easier, right? Because the printf is the vulnerable function has its stack frame first, then printf's stack frame is lower, and that %n, %x, whatever will look for items on the stack at a higher address, and eventually that will go to the address where your input is. Yeah, so that's a tricky part. Okay, I guess that's it for today. I will post the homework soon. Next week we will learn return-oriented programming, which is a lot of fun. Like I said, I mean, even though right now all of you are good hackers, you find you can solve all the challenges. Then the return-oriented programming will teach you something you probably never thought of. Imagine that the format string, the buffer overflow was discovered in the 80s, and the return-oriented programming was discovered in 2009, 2008. For 30 years, 20-something years, no one discovered that we can. So before that, we are developing all kinds of shellcode, right? We develop shellcode. You develop shellcode. Then for 25 years or even longer, no one realized that we don't need to inject shellcode. We can just wave the bytes, the random bytes in the memory, wave them together, and they can be arbitrary code. They can be our shellcode. That's so the first time you say that, you'll feel, oh, this is really crazy. Okay, it has been 15 years. This has been discovered. So yeah, so we are going to do that next week. Okay, cool. Thank you everyone for being here. See you next week. I will make sure I will be there in person. Okay, bye.
Thank you.
Thank you.
Thank you.